Okay, so next I'm gonna continue on this example problem, which is on page 229. Example 20. I did not add a video last time, so hopefully this is gonna help you out. So we left at the solution part. We have our we set up everything else in terms of the layout. So for the solution, again, first thing we do is we start with our energy conservation. Okay, so this equation is kind of the first step one. And after that, we think about, can we simplify this? So is there anything that is zero? It starts from the left to the right, so kinetic energy. We know that we are trying to find the velocity in part B, so we have to keep the kinetic energy term because that's related to the speed, the velocity. And then next I think about the delta U. So delta U is all about elevation change, okay? And if there is a change in elevation, then you may want to keep that, or you can also still ignore it and then write the work done by the weight force on the right side. So you still will get it two options, but in this case everything happens on the horizontal, right? So it goes along the x direction. That means there's no change in elevation, it's horizontal. That's why delta U will be, so I'm gonna take this and say delta U will be 0, and the reason is there's no change in elevation. Okay, next is delta I. So delta I is also 0 if there's no change in temperature or pressure change. There's no change in temperature or pressure, and because of that we're gonna get rid of delta I as well. Next thing is work, and as I've been doing it so far in a couple examples I've shown, I do skip this part and I will investigate the work done in more detail later. So I'm going to move on to the heat. Heat, do we add or remove any heat from the system? No. So that means this term is going to go to 0 as well. So please make a habit of explaining those, okay? You can do it as I do it before, like I just cross them to 0 and quick things, no change in elevation, no temperature or pressure change, no heat or something. So in parentheses you can show them and understand the topic that way better. So work contains all forces except weight force, because first of all the weight force is not doing any work, and if it was, we would keep potential energy, and we're saying there's no change in potential energy because there's no elevation. Okay, but you can still kind of think about the first free body diagram. There are three forces, and for the work term, so if you simplify it, first of all, this is what you get, this equation here. If you look at Wiley, that's why I don't really like about Wiley, especially in this topic. They keep writing different equations. They all come from this general energy conservation. They call this work energy theorem. But the assumptions may not be very clear to you. So again, if you do it the way we're showing you in this book, I think it's really helpful, and then you don't make a mistake and you don't need to memorize what the work energy theorem is. Okay? So the kinetic energy is equal to the work done, and that's what the work energy theorem is all about. Okay, but again, no memorization needed. You just get this because you understand the topic, and then you know which ones are 0. Simplify, get this equation first. Okay, next is again focusing on the work term. Draw your free body diagram, okay, and write down what the work is. You have 3 terms in it. So the weight force and the normal force is going to be 0, and I usually write down why. Because of the displacement, right? So if we go back to the figure, we are compressing it and then letting it go. So the object is going to go to the right along the x direction. So as I mentioned before, I usually show the displacement direction next to the free body diagram, just to give me an idea, because I'm thinking about work done by maybe the weight force, and I can easily see that weight force is perpendicular to the displacement. That means angle is going to be 90 degrees. That's why there's no work done by the weight force. And the same reasoning also applies to normal force in this case. Since normal force and displacement are 90 degrees, when you find the work term, cosine 90 will give you 0. Okay, so kind of make a note of that as well. And again, it says it here. Then we just have one term left, right? So we're going to think about that. And the work by the spring is, we already found this, right? This is the equation. It's in the equation sheet as well. And we can find out what the work done by spring force is. So since the reason we cannot use this delta K equals to W, which is the work done, total work done equation, to find the spring work done, because we don't know the velocity. That's the second part, right? So we're just going to use, we have two equations, right? Equation number 1 and 2 for part A. The first equation has more than one unknown, so I cannot use that. So for part A, all I need to do is just write this equation. X initial is -2, and those x's are positions, so you have to be careful with the positives and negatives. But the good news is, since you're scoring them, they're gonna go away anyway. But definitely keep it, as we show it here too. Keep the negative signs. Just make a habit of thinking whether they're compressed or stretched. That kind of helps you out to figure out the directions of x, the displacement, and the force. Okay, so since we are scoring and final, it's gonna come to the relaxed position, so x final becomes 0. That means this term goes away, and 1/2 kx squared will be simply 2 joules, as we were expecting it, and it is also positive. And the work of the spring is the total work. So there's no other work done, as we also showed that earlier. So to be able to find the velocity, we are going to use this equation number 1, delta K is equal to W. Again, W is the work done by the spring force only. And we already know what the right hand side is. So left hand side, if you open it up, it becomes, since it's the change, it means always final minus initial, never the other way around. So kinetic energy is 1/2 mv squared, and taking the difference, making it equal to the spring force, will give you this relation here. And then just plug in the numbers. Initial is 0, this term is gonna go away, and then you're gonna end up with this relation there. When you plug the numbers in, you're gonna get the velocity to be 2 meters per second. And also please check the units too. So how do you get from joules to meters per second, for example?